Good morning, ladies and gentlemen, boys and girls. I want to clean up a few things about logistic curves. I have two more short videos on logistic curves. I might watch these. We're going to be talking about some assignments that deal with these, but certainly we'll be doing some free response questions. Before I get to talking more about this differential equation, this logistic differential equation, I just want to review a little bit about what the derivative graph says about the original graph and the second derivative graph says about the original graph. So this is actually out calculus 1 topic. This is F prime short story. And what we're going to do is talk about this red graph right here, which is going to be F. And I have F where F is increasing. It increases to that point right there. Then it decreases to that point and it increases. So I have a maximum point there and a minimum point there. And I know from F prime short story that when F is increasing, the first derivative is positive. So the graph of F is increasing from here to this x value and is increasing from this x value here. So on those two intervals, from here and here, if you will, F prime, the graph of F prime better be positive. And if we see right here, F prime is decreasing. So from this interval to this interval, F prime better be negative. And so it is, and so we can come down here and we can sketch the graph of F prime. Here's F prime. F prime is positive above the x-axis. That's positive. It's negative below from here to here. From here to here, the F prime is negative as it is, and now F prime is positive. So this gives us a good picture of F double prime with respect to this particular F. Okay. The last thing I want to do is look at the second derivative. And if I look at the second derivative is the derivative of the first. This guy right here this is the first derivative. Boy, that'd be confusing. That's the first derivative. And so I'm going to look at the derivative of the derivative, i.e. the second derivative, and hey, what am I doing? This particular graph here, what's this thing doing? Decreasing to that point, okay? And then it's increasing right here. So on this interval right here, if I want to create another interval, I can. What do I know? I know that since this is F prime then, F double prime of x is going to be less than 0 right here, as it is down here. This is where F prime is less than 0. And from this point forward, I know that F prime is increasing. What does that tell me? That tells me that F double prime is greater than 0, as of right here. And the one connection that I'm going to make between the graph of F prime here and the graph of F double prime is this minimum point of F prime happens, we call this the inflection point of the particular graph. So that's exactly where this happens. That's where this graph here, the original F, has an inflection point. Because it's where it changes from concave up to concave down. And I'm going to look at these three aspects when I start talking about this logistic model. So I'm going to go back here and I'm going to go to an example. Here I have a new logistic growth model right here. This is called the logistic growth curve, part 2. And I have this, and there's a couple of parts of this that not confusing again. Well, it is kind of confusing, but we need to clear it up. So I have my growth model, and my growth model is a function of t. This is a function of t. These are t values here. And this, the y, the horizontal, that gives me my population model. And I know from previous examples that I've done that this 150 better be my carrying capacity. It is the carrying capacity. So I can make a horizontal line there, bring it down here, and that's the carrying capacity of my particular model. Okay, let's sketch that. And so this is going to be, this is where the population is going to equal 150. Okay. And what do I know about this population, this growth model? This thing is always increasing. This is always increasing. What does this tell me? This tells me that, by golly, the derivative of p with respect to t is always positive, because this graph is always increasing. And so what I want to do is, first and foremost, I want to just do a quick algebra, a few algebra steps, and I want to turn this is 4.3 minus t. I want to turn that, I want to make it look like this as our 1 plus a e to this negative mk t, and that was given in our video yesterday. So I want to look at that, because right now it doesn't look like that. And you might have to pause the video and see what I'm doing here. What I'm doing is taking this e to the 4.3 minus t, and I'm separating it to e to 4.3 times e to the negative t. This creature right here, this is my a here. Okay, and this negative 1, it looks like this is negative t, so it looks like my mk is going to be just 1. Okay, so that's all I've done is rewrite the growth model to make it look like the growth model we were accustomed to in our notes from a previous video. All right, so what I want to do is talk about the graph of this guy right here. And what's funky about a logistic differential equation, what's funky about dB dt, is this is normally given in terms of the population. This is not given in terms of as a function of t. This is given as a function of population, which is very, it's going to present some problems, but we're going to clean them up today. So this is just what I know. These are from previous notes. If I have a population, okay, this is the formulas. These are the two formulas that I gave you. And what I want to do today is I want to take this population model that I was talking about on the previous screen, and I just want to find this guy right here. I'm going to find dp dt given this model. And it's easy to do. I mean, I could differentiate this, but if I do differentiate it, I would have to differentiate it in terms of t. And I don't really want to, because I want to investigate this differential equation right here. And this differential equation is in terms of p, not in terms of t. This right here is not a function of t. We could make it a function of t, but it's going to look very complicated. Okay? And this would be a differential equation. We're not going to ask you to go from here to here, although it's quite easy if you know the formula. And you do, you can always use your notes. All right, so here we go. Here's the model that we have. And like I said, if I look here, this is negative m times k. Well, this is negative 1, so that tells me right here 1, this 1 right here, this 1 is equal to km. We know what m is. M is 150, so k is simply 150, 1 over 150. That's what k is. So I'm going to take this k, this 150, put it in here, and I know what my m is, and that's going to give me on the next slide, I'm going to actually come up with dB dt right here as a function of the population, and here we go. So, all right, so here is my guy, rewrote it, and here is my dB dt. This is kp max minus p. This is the derivative of this population. Keep in mind, this is not given as a function of t. This is given as a function of the population. And we can look at this graph, and this is what we did before on another video. We can look at this graph and see when is the derivative going to be 0? Well, the derivative is going to be 0 when the population is 150. And that's why it's one of the biggest reasons why they give us this way. So if you see a differential equation looks like that, you're going to know it's a logistic growth model. And you're going to know that it has a maximum population as 150, because look at here. That's where the derivative That's where the slope of the tangent line goes 0. Right there at y equals 150. Or not p, but when population is 150, that derivative is 0. And again, look at this. That population is 0 again. Where? When the population is 0. It's going to start off 0. Going to go like that. It's always increasing. So it's always going to be positive. And I have actually, with my graphing calculator, and I'm not going to show you how to do that, I'm just going to relate the graphs. This red graph here, ladies and gentlemen, this is the graph of dBdt. dP dt is a function of t. Oh, always increasing. My function is always increasing. The derivative better be always positive. Well, guess what? It is always positive. Didn't I? Yeah. The derivative is always positive. Which one was I looking at? This guy right here. The derivative is always positive. Okay? The derivative, this derivative is always positive. But it has this, what's going on here? It has this maximum point here. The derivative has a maximum point. That's where, keep in mind, what is a derivative? It's the rate that the population changes. dB dt in this case is the rate that this population changes. And when the rate, which is this guy right here, is the greatest, when the rate is the greatest, guess what happens? That happens precisely at 1/2 of the maximum population. So this, if I did a vertical line, and I did this on a previous graph, that would match up right to that. Guess what? That's going to happen right at this inflection point. Right at the inflection point of the population model. That's when we see this graph, the population is increasing, increasing, increasing. Still increasing. The rate is still positive, but it's increasing slower. And that's what this graph means right here. Okay, and we looked at that. What I want to do is look at, hey, golly gee, let's pull this out of here a minute, get it out of our way. Golly gee, what would the derivative of this rascal look like? I.e., what we want to know then is what would this guy look like? The second derivative of p with respect to t. What does that look like? And we're going to investigate that on the next slide. Here we go. Okay, so I have the original. All right, well, so let's look at that. This graph has a maximum point. We know at the inflection point is a maximum point. Hey, what's going on here? The second derivative is increasing. Pardon me, the graph is increasing. So right here in this interval right here, what do we know? From here on, that the second derivative, by golly, the second derivative better be greater than 0 because this is increasing. What do I know from here over? Well, what do I know? The second derivative, ladies and gentlemen, better be less than 0 because it's decreasing. The other thing I know is what is the derivative? If I think about the second derivative as being the slope of the tangent to this red graph here, what's the slope of the tangent go as t goes to infinity? The population is going to the maximum value 150. So what's going to happen with this second derivative? As these two things happen, the second derivative, by golly, is going to do what? That thing is going to 0. Okay? In like manner going this way. As t goes to 0, the population is going to go to 0, and the second derivative is going to go to 0 as well. So, and the second derivative, since the first derivative has a maximum at this point, there's a maximum there in the first derivative, we know it is. The second derivative is going to go from what? The second derivative is going to change from positive to negative. And here's a nice picture of the second derivative. Okay, right here at this point right here, ladies and gentlemen, I can do this with that point right there. That is going to be where the first derivative has a maximum and where the population has an inflection point. Okay, this is the graph of the second derivative. Okay, and what's happened is t goes to infinity, the population goes to 150. And what does the second derivative do? It continues to go closer and closer to 0. In the same way here, as t goes to 0, because the model doesn't exist when t is less than 0, but when t goes to 0, the first derivative, the slope of the graph of the first derivative is going to go to 0 as well. And what I've done is, and keep in mind this graph here, and this is what's confusing, this graph here of the second derivative, this is also a function of t. But guess what? We're not going to give it as a function of t. We're going to give it as a function of p. So I'm going to show you this next slide, and this actually has, whoopsie, this has a computer analysis. This I did with my graphing calculator. This is the actual graph of the first derivative and the second derivative, but as functions of t. So the red guy here, let's get him out of here. The red guy here is dpdt, and this black guy for this instance is the second derivative of p with respect to t squared. And now, on my first video, I made a slight error on taking this derivative, and I wanted to fix that error up right now. And before I can tell you how to fix that error up, I'm going to have to review implicit differentiation. So here is, I'm going to insert a blank page here. Okay. If I were going to differentiate, if I had y is equal to y squared, or anything equal to y squared, or let me write it this way, please. If I wanted to differentiate this guy right here with respect to x, I'm going to have to use the chain rule. This is a review of implicit differentiation. You'll have to look this up in your notes. What is this? Well, this is going to be 2y times dy dx. In like manner, if I'm going to differentiate with respect to t, anything, I can just go y squared again. That's going to be 2y dy dt. So if the variables don't match up, I have to add this dy dt on the end of it. And that's what I did not do on the first video, and I'm cleaning that up here. This is what I wanted to do. This was my first derivative here. What I want to do, my objective, is to find the second derivative, so I'm going to differentiate this. I want to differentiate this with respect to t, okay? But before I do that, what I'm going to do is I'm going to multiply through by this 150 over p, and I did this on another video. 150, 1 over 150 p times 150 is just p. These turn to 1. And this is going to be negative 1 over 150 p squared. This is what I'm going to differentiate now with respect to t. And what is the derivative of this guy right here? Well, I'm going to differentiate the inside with respect to t. What's the derivative of p? 1. What's the derivative of minus 150 p squared? Well, you're going to bring the 2 down over 150 p. But what I didn't do on the other video is I didn't add this dp dt. And we know what dp dt is. It's this guy right here. So I have to add this to the end of this, okay? And right here it is. This is my dB dt, okay? And now if I want to analyze the second derivative, I want to know where that second derivative is 0. So I have three factors of the second derivative. I have this factor, I have this factor, and I have this factor. And that's interesting. When is that second derivative 0? Well, that second derivative, this factor is 0 when p is 150, easy enough. This factor is 0 when p is 0. This factor is 0 as p is 75. Oh, half of the maximum population. And if I split my domain, and my domain basically is going to be, my population domain is going to go from 0 to 150. If I review that graph, my population is only going to go from 0 to 150. So I'm going to do some test values back here on that, only from 0 to 150. And where does my second derivative then happen? If I want to go from 0 to 75, sorry, these are my test values. I'm going to keep in mind I'm only going to, I apologize for that. I got a new pen that's very, very, very touchy. If I only look at this interval right here from 0 to 75, if I put 50 into this, if I put 50 into my factor form, let me get this out of here so I can look at my factored form. These are all going to be positive if I put 50 in. 1 minus something less than 1 is positive, positive, positive. What does that tell me? That tells me that the second derivative is greater than 0. And that tells me that the first derivative is increasing. If I put 100 in, if I just take a test value between 75 and 100, 75 and 150, use 100, then it's going to be positive, positive, positive. Well, it's going to be, if I put 100 in this guy right here, if I put 100 in this first factor is going to be negative. That factor is going to be positive. This factor is going to be positive. The third factor, looking at this factor form, the second derivative, and that's going to tell me that the second derivative is less than 0. So here dB dt increases, dB dt decreases by the first derivative test of dB dt. And what happens at 50, the first derivative, the second derivative is going to go to 0. And this would be analysis of how I could come up with this graph right here. So a lot of information here, mostly what we already knew. When I originally, the reason why I did this is just going to help us create this, the graph given the differential equation. But what I mostly wanted to do here was to explain to you what would happen if you differentiated this guy right here. If you differentiated the derivative with respect to t, you have to add this dB dt on because of the implicit differentiation. That's the error that I made in the first video. So that cleans that up. I'm going to have one more video about how to come up with the graph of a logistic curve just given the dB dt, the dP dt, the differential equation. But for right now, I would watch this video, get what you can out of it. I will have some assessment type problems, some free response type problems to go along with this. Other than that, good day. See you soon.